On data-driven education and athletics outreach. I'm joined here with McGyver Clark. He's an affiliate professor at Brigham Young University, and he's going to be reporting on just the second quarter of a 5-year project, an exciting development on using AI and data to really dive into track and field events. Now, McGyver is the coach of American Heritage School in American Fork, Utah, the head coach for both the cross country and track teams, and also the former coach at Timpview High School, where he led the Timpview team to several state championships, and also a coach from early on of Jane Hedengren, my daughter. I'm grateful to him for that as well. He has a lot of experience working with athletes and using data-driven methods to help them reach the next level. So with that, I'll go ahead and turn it over to McGyver Clark.
Thanks, John. And very excited to present on our data-driven engineering project. And so this project is a 5-year project. Its goal is to help students, number one, develop artificial intelligence and machine learning tools. 2, to be able to apply that into an athletic space. And 3, be able to communicate technical details to non-technical audience. And so we are starting from the ground up with these students, developing AI technology, applying it in an athletic space, and then we are getting these students to participate in our outreach program, which then helps them take the technology and give it to the end athlete, which is high school athletes and college athletes. And so that's the goal of our program, is to teach these engineers how to develop technology and then to present these technical details, the technical data, to a non-technical audience. And so we're going to present some of the mentors that are helping these students develop these event-specific technologies. And then we're going to show the student showcases, so the progress that our students have made, and then some accomplishments overall for the project. And so some of our event mentors are Scott McKeel, a local physical therapist here in Lehigh, helping us with the distance running analysis. Jamie West, she is the hurdle coach at Layton High School, as well as the head coach of West Hurdle Group, one of the best high school private clubs here locally. She coaches some of the best in the state here. Zach Stetler, he's the strength and conditioning coach here at BYU. He already works with the BYU sprinters as well as the other track and field athletes, and so he's helping us with the sprints. And then Danny Wilkerson, head coach at Bethel University, as well as the USATF representative for the pole vault. Here are some of our students. So we have groups for sprints, hurdles, discus, distance running, and a few on the next slide. And as you can see, many of our students are BYU student athletes. So they are competing in respective spaces, as well as they are engineering students. And so they are learning how to develop this technology from the ground up. We also have a pole vault group, wearable data, and we are incorporating language models into everything we build. And McKenna is our outreach assistant coordinator. And so she is helping coordinate these visits for these students to go take what they have built and communicate that to high school athletes. So first, we're going to present on some of McKenna's work. And so in our outreach program since January, we have visited and reached over 750 athletes in the state of Utah and Florida. We have visited 19 teams, and that is on our way to our goal of 30 teams in the year 2025. So our outreach program, what does it look like? We go and visit these schools. We take videos of each athlete. We process these through our AI tools, prepare personalized and team-wide recommendations, and provide data-driven training guidance and recommendations for how they can improve. Overall, this program has been phenomenally successful. We've had amazing feedback on how the program has helped inform them on making decisions to improve their training for their athletes. So now for the distance running, so we are using AI to analyze different biomechanic metrics. The lateral pelvic tilt is one of the major contributors to injury in distance runners. Now we have built tools to automate the measurement, and we will be also measuring about 14 other features that predict injury as well as predict optimal running form and efficient running form in distance running. So here's a little demo of what the students have created. And so here's a simple hip dip analysis where we are detecting the tilt of the hips. It is near real-time processed, and then we give the user overall and summarized statistics. So we can see average hip dip angle, and we can see the difference between the right dip and the left dip. And we display it in a simple and graphical interface. The next group is the discus throw. So we have Heather and Creed on this analysis. And so here the students have summarized the different stages of the throw. And so we have preparation, single support entry, and etc., all the way to the reverse out and exit of the throw. Here's some of the progress. They have done a literature review of choosing feature measurements that are the most important, and they have developed a initial application that can measure different trunk angles at entry point, X and Z angles. Now they are going to implement multi-camera systems so we can catch all the angles, especially the ones that are covered up with the spin movement. They'll finalize method, and then they will make an AI integrated application for use. And so some future metrics that they will be working on are some torsion metrics. So the separation between the feet axis, hip axis, shoulder axis, essentially measuring how much twist can we generate and how much can we unwind to generate that force into that discus throw. So here's Valerie Allman, two-time Olympic gold medalist, and she is one of the best technicians in the sport. And so they have used her to analyze how she throws, and then we are generating feature statistics on that data that we receive just from the video. And now one point to make sure to give is that everything that are generated has no help materials or aids. So this is all AI generated pose estimation. So the next group is our hurdle group. So this is Violet and Davin. And so part of the hurdle stage is you have about 3 stages of that hurdle. So takeoff, hurdle clearance, and touchdown. Here's what they have completed. They've created a base Streamlit app. They have processed that data and analyzed and automated when the individual is over that hurdle. And now they are working on creating these feature methods, working with Coach West. They'll adjust and improve and then display that into an AI integrated application. Here are some of the measurements that they will be measuring. Trunk angle at takeoff, lead knee angle, lead elbow angle, center of gravity height above hurdle, horizontal distance from center of gravity to touchdown, and trail knee angle after touchdown. All of these metrics are simple, measurable, and predict efficient force transfer in and out of the hurdle stages. Here's a small demo of their application that they have, to where they take the video, they process it with the AI algorithm, and they allow you to have a data dashboard and to analyze at what stage and what metrics at the different stages of the hurdles are. And so great job, guys. Okay, here's our sprints group, Dallin and Zarek. So in our sprint analysis, we are getting both biomechanic and velocity data measured. The analysis is working well, and this is already deployed into our outreach program. The processing is now completely mobile, and we are working through accuracy issues and calculating distances and velocities. And so you can see here in this video where we use 2 simple cones, and as the individual runner passes the plane of the cones, we start that flying 10 time, and that flying 10 time gets processed. We get that velocity metrics, and then we also can see the biomechanic data with some large language model incorporation. And so as the individual is running, you can see on this diagram here is the camera. Here's the beginning of the flying 10, and here's the end of the flying 10. And so as we're measuring distances in space, this equidistance circle here is that Z depth axis that we are measuring on. However, we want to convert it to this horizontal and parallel plane, which the runner is running on. And therefore, about here is where our distance measurements currently are accurate at the mid stage, about 5 meters into that 10-meter fly. However, if we take measurements from the beginning or end, we are seeing inaccurate data. And so we are working on ways that we can convert this Z-axis into a measurement that is applicable, understandable, and accurate. So here are the different stages of the sprint. We have the golden position here, we have touchdown, we have the recovery phase, and we have the different types of swing phases as well. So here are some of the different measurements that we already measure. Maximum hip angle, the knee separation at touchdown, maximum knee flexion, how much is this heel up into the tail end, the stride rate, so your cadence as well as the ground contact time, how long you're spending on the ground, trunk angle at touchdown, takeoff trunk angle, and toe velocity at touchdown. We also measure your flying 10 time and max velocity in this analysis, and it is all automated through AI. All of these things, for sprinters, it is paramount to reach certain positions, certain angles, reach certain velocities and certain forces. And this is how we are going to help coaches understand what their athletes need to work on. And then they can build personalized training plans to help athletes in a personalized way. So here's another part of the analysis. We do automated step detection. And so you can see here that this has been automated for this data. We can extract the steps, how long their feet are spending on the ground, what their stride rate is. However, sometimes we do see this error in the data, and therefore we have to add some manual entry components. And so now we have built that into the front end of the application to where coaches can add in manual entry and therefore can get accurate step detection, stride rate, ground contact time, as well as accurate touchdown and takeoff metrics that are built on top of that data. And so the students are working hard to fix some of the inaccuracies in the distance and velocity measurements, and it'll be very soon by the time that they will have that taken care of. Okay, we're moving on to the pole vault analysis. So Marcus has been working with Danny Wilkerson at Bethel University, and they have summarized the pole vault into different stages. So we have the approach, plant, takeoff, swing, turn, and fly away here. And so here we are using some color detection, and where we put tape on the pole, and what we're measuring is lack of the angle of the bend, but more of the total pole cord distance. So this distance between the two ends of the pole, we're measuring that distance. How much is the pole bending? The more force you put into the pole, we can model it as a spring, and as that spring is added force to the spring, then this pole cord length is going to be minimized. And so here we can see that it is about 77% minimized. And so we're working on other metrics with Danny, and Mark's doing a great job at working with him in summarizing the pole vault and extracting useful information to optimize that pole vault event. Okay, now we're going to go into Oliver. So in all of what we're doing, we want to be able to communicate this data in a way that's simple, understandable, as well as have a question and an answer interface for the user, and then to answer the question, what now? So when we give all of this data to an athlete or a coach, we want an fully systematic and integrated way that we can aid the user in making those training adaptations that will end up making the bigger difference in improving those metrics overall. So here is our data pipeline. Okay, so we are using currently Retrieval-Augmented Generation, or a RAG pipeline. And so we collect peer-reviewed documents. So these are textbooks, studies, and other training and coaching resources, and we are collecting them. And this is going to be our source material in generating any answers with the LLM. And so we have a user query, so the user will ask information, and we put these peer-reviewed documents into a vectored database. We're going to use some machine learning to get chunks of information that are applicable to that user query, and we're going to use those applicable source materials to generate that language response so that it is accurate, peer-reviewed, and we won't deal with any of the hallucinations or misrepresented or ill-informed responses from LLMs from its general training. And so here's our RAG pipeline. We are testing different models, and Oliver's done a great job at testing models. So we're asking it questions, getting answers, testing different models on things like relevance, understanding, clarity, and quality. And so not only can we choose right models to base our automated trainer recommender, but we're also going to be fine-tuning it so that it ranks high on these benchmarks, that it will be a reliable and high-quality source of information. So the goal with this, like we said, precision metrics, effortless data access, continuous improvement, and integrated support in a holistic development environment. And we want to be testing this, and we want to be integrating this into every one of our tools, so that the users have the maximal information and the best information that we can give them on the event-specific analyses. Okay, now we're going to move on to Luke with wearables. Okay, so currently he has developed a web app that processes FIT files. So FIT files is the industry standard in measuring things like pace, heart rate, distance, time, intensity, or work into and any sort of watch data, workouts, etc. And so we have created a file upload to where when an individual on the Garmin app uploads a file, that API alerts us. An API is just an integration into a database on a specific app. So Garmin will tell us, hey, a new file. Our system extracts that file, and then we process it, and then we can pull the metrics and we can analyze it in a systematic way. And then what we want to do is incorporate that into the biomechanics and into race performances, into sleep data, into heart rate data, etc. And so we can have a holistic data pipeline to where we can build analysis tools that are holistic to the athlete, not only from computer vision. And so here is Luke's demo. And so he has a couple athletes on his team here, and you can choose it, select the athlete, and then it will give you summarized data from the Garmin API. And then what's really cool is that we can do work periodization analysis, and so we can see how much work are you doing, is it at the right time, right? And so here he has a mileage variability chart, and so if it's increasing or decreasing too much from the average, then we're going to highlight it and inform the athlete that we might be able to make more informed decisions on our training. So those are our groups, and we're very excited about progress. And so overall, here is our 6-month update, Q2 update. We have 4 world-class coach mentors helping our athletes build these event-specific analyses, and to make it to where we're merging the wealth of knowledge that these coaches and mentors and a physical therapist have, the wealth and experience they have, with the data-driven approach where we are taking optimals and we're merging those two worlds. We have 11 undergraduate researchers here at Brigham Young University, all engineering students or in some form of computer science and data science. and they are researching these areas actively and building this technology. In the chemical engineering department at large, we have 52 graduate students that have developed apps, and they are learning how to develop apps, how to process data, how to visualize that data, and how to build data apps and dashboards that process it, visualize it, and give key information to stakeholders to make decisions. We have analyzed over 750 athletes, and we have 2,400 active web users on our applications thus far. So thank you guys so much for everything that, watching us and supporting us. And thank you so much for this update. And I will turn the time back over to John. Thank you.
That you've made. I just want to highlight, just as we close here, the Athletics and Data-Driven Engineering webpage and just some of the objectives. This is our long-term view for the 5-year project. We are working on cultivating this innovative research environment that equips these students with skills in data science, machine learning, data visualization, and interdisciplinary collaboration. We're excited to work with several of these advisors. If you're watching this video and also feel like you have something to contribute as well, please reach out. We'd love to attract additional expertise, additional resources to the team to be able to build this over this 5-year project. And there's a little bit of additional information here. We'll post this presentation here as well, and a little bit more about some of the long-term community resources that we're developing, both for making things available and open source, but also to be able to create tools that athletes and coaches can use on a daily basis as part of their training programs. So that's just a little bit about the program. We're excited about the development so far and look forward to see where this will go over the next 5 years.